This is 9.2 applications of differential equations, and here are 3 models of growth. So if you want to take a little second to write all of this down, please do, because this is really important. And I'm mainly going to be doing, I'm going to start off with a little bit of where did this differential equation come from, and also what are the solutions to some of them. I won't do all of them, but you'll at least see some of them. So take a little time to just pause the video if you want to and do them. So, with these types of differential equations, we have 3 different types. We have unlimited growth, limited growth, and logistic growth. So I'm going to talk a little bit about each of them, mainly the logistic, but I won't probably do the solution because the solution, I'll probably put it on the link below on the comments or something, a link to how I derive the logistic, because the logistic can get really, really long. So let me talk about the first 2. So, but before we start, let me go ahead and talk about proportional quantities. So proportional quantities. So what this means is that we say one quantity is proportional to another quantity if the first quantity is a constant multiple of the second. Okay, so that's what it means to be proportional. So when I say that this is proportional to something else, we just say that one quantity is proportional if the first quantity has a constant multiple of the second. So you probably have seen in some college algebra class that y is proportional to x. Well, basically what that means is that you have y equals ax. So basically the relationship between between x and y is just by a constant a. So here a is what we're going to call the proportionality constant. Okay, so that's basically what it means. In algebra, you usually maybe have seen k, so it doesn't really matter. That's basically what it means to be proportional. Let me just first start off with the first type of growth, which is unlimited growth. Okay, and unlimited growth is actually something that you have seen before in other previous classes, but you probably never spoke about it this way. So unlimited growth. And basically what unlimited growth is we're talking about the first type of differential equation. So I'll go ahead and give you a little setup of how did this come up. So basically this is what unlimited growth is. So if a quantity y grows so that its rate of growth y prime is proportional to its present size. Present size, let me just call that y. Then we can write it this way: y prime is equal to a y. Okay? So basically what I'm saying here is that the rate at which y is growing is proportional to its present size. Okay, so y prime, remember, is the rate of change. This is a derivative, so rate of growth is proportional to the present size. Okay, so how large this is initially. Now, is this a really good way to kind of explain this? Okay, is this a really good assumption? Well, let's take an example for this type of unlimited growth. So let's say I start. Whoops, that's not how you spell start. So let's say you start with 1,000 bacteria. So you have this bacteria colony, and the growth is growing at 300 bacteria per hour. So maybe you have this, you're a biologist or you're a researcher and you have 1,000 bacteria, and every hour you're getting 300 additional bacteria. Okay, so now let's say that I add 1,000 bacteria into these 1,000 bacteria. So now what I'm going to have is 2,000 bacteria. So if I have 2,000 bacteria, then my rate of growth is now going to be 600 bacteria per hour. Because if this is growing by 300, then I'm going to have an additional 300 in 1 hour. Well, these extra 1,000 that I add is going to be an extra 300. And 300 and 300 is just going to give me 600. So that, I guess this is going to be a good assumption, okay? My bacteria are just going to be continuously growing by some factor A, okay? Where A in this case is going to be the proportionality constant. So what is the factor? Well, in this case, it's going to be doubling, right? Okay. There's many different ways that you can kind of figure out this value of A, and we're going to try to figure it out as well. But basically, if you have unlimited growth, so if something is endlessly growing, okay, for unlimited growth, then the differential equation that we can use to model this is going to be y prime equals AY, okay? So now what we're going to do, I'm going to solve the differential equation for you. So let's just go ahead and solve it. Okay. So what we're going to do, we're going to change this y prime to dy over dx. Okay. But it's not going to be x because we're talking about time. So it's going to be dt. And then this is going to be equal to ay. Okay. We're going to use separation of variables. So I'm going to move the tt over. So I'm going to have dy is equal to ay dt. And then I'm going to move the y over. So I'm going to have 1 over y dy equals a dt. So now what I'm going to do, I'm going to apply an integral to both sides. So this is going to give me natural log of y. Now we said that the natural log of absolute value of y, we're going to get rid of the absolute value because we've seen that it's just going to give us constant every single time that we do it. So this is going to give us a t plus c. Okay, we're going to exponentiate, take an e to both sides. So we have that y is equal to e to the at plus c. We already know that we can change this up to y equals e to the at times e to the c. This guy's just going to be some constant. So y is equal to c e to the at. So this is a solution to this differential equation, which means that if I have a differential equation that's being modeled by unlimited growth, then that means that I don't need to solve it anymore. I already know what the solution is, and that's why I made you guys write this in the very beginning. Here is a solution, okay? You don't need to do it anymore, okay? Now, what is that value of c? Well, that value of c is the initial condition. So at time equals 0, you're going to have c amount. So this is kind of like if you think about the initial population. Initial population. So how many do we have initially? And this actually should look a lot familiar to you, especially if you're taking pre-calculus. You maybe have seen y equals PERT, so y equals PERT. This is actually the same exact formula, okay? We've used this for investments. We've used this for rate of growth, maybe decay as well. So this actually is just this derived from a differential equation, okay? So this didn't come out of nowhere. It actually was found from a differential equation. So this is the first one. Initial population is going to be your initial condition. This is just a solution. So I'm just explaining a little bit of this. When do we use this type of problems? Or, when do we use this differential equation? Here I gave some examples. Kind of, you can see the graph is kind of exponentially growing. It's starting at the initial population. And then some examples are just investment, bank accounts, and unlimited population. Okay, so now let's talk about a little bit about the limited growth, okay? Because we know that a limited growth, this means that it's growing exponentially. It's continuously growing and growing and growing. And we know that that's not true, okay? Nothing's going to continuously grow forever, okay? So another type of differential equation is what we call limited growth. Okay, so we have this limited growth model. And what we basically say is that a limited growth is not really real. Okay, so we have some restrictions here. Okay, so some restrictions here is that you have food scarcity. Okay, space, the lack of space. Okay, you might have some predators. So, for example, we know that this was maybe some sort of animal kingdom, we know that this is not going to grow continuously because we know that there's lack of food, there's lack of space, there's predators that might be hunting down these animals. So we know that this is not going to be unlimited. One cannot have an infinite amount of people or animals or whatever we're looking at. Okay, so a model like this might not be very suitable for what we're looking at. Okay, we may have to incorporate these additional variables. Okay, so what we can say is the following. So say y of t cannot get any larger than a certain fixed max size. Okay, so there is a maximum, okay, that you can there's a ceiling. You cannot exceed this, and then we're gonna call that m. So a way that you can think about this is that that this particular y of t is proportional to the max size m. Okay, so it's proportional to the max size f, m minus the present size. Okay, and always with these types of problems, we're going to assume that the growth starts at 0. So initially we have nothing. Okay, and a way that we can kind of try to write this differential equation is that the rate of growth is directly proportional to the size of it. Okay, the maximum size minus the present size. Okay, so this is what we have. Okay, and we're gonna say here that y of 0 equals 0. Okay, initially we have 0. Okay, so how do we go ahead and do this? So all we're just doing is that we're taking the differential equation. The rate of growth is just proportional to the differences between the maximum size minus its present size. Okay, so this maximum size, think about it as this is just the upper bound. Okay, for this one, let me go ahead and solve it for you. Okay, we'll go ahead and I'll give you a solution to this one. So we're gonna write dy over dt is equal to a m minus y. Okay, I'm going to move the dt over, so I have dy is equal to a m minus y dt. And let me move the m minus y over, so I have 1 over m minus y dy equals a dt. We're going to take the integral to both sides. Okay, this is just going to give me the natural log of m minus y, and because we're taking the integral with respect to y, there's a negative, so that we're going to have a negative on the outside. This is just going to give me a t plus c. We're going to divide by this negative. Ln of m minus y is equal to negative at. This is still a constant. Take exponentiate both sides. So we have that m minus y equals e to the negative at plus c. Okay, we already know what this guy is. M minus y equals e to the negative at times e to the c. This is just going to give me another c. So m minus y gives me c e to the negative at. And then we're just going to subtract by the m. So negative y equals c e to the negative at minus m, and then divide by a negative. So y equals negative c e to the negative at plus m. Okay, let me switch these around so that the positive comes in first. Okay, so this is my solution. Now, how am I going to solve for this c? Okay, because we need to figure out what that c value is. Well, we know that our initial condition in the beginning we're imposing this initial condition that in the beginning we have 0. Okay, so we're going to have y is equal to m minus c e to the negative a times 0. This guy is just 0, m minus c, and this thing is just going to be 1. So if I move the c over, I get c equals m. So my differential equation is going to be y is equal to m minus m e to the negative at. I take out an m, and I'm left with 1 minus e to the negative at. So this is my solution with initial condition y of 0 equals 0, okay, for limited growth, okay? So if I wanted to go ahead and explain or model something with limited growth, then this is my differential equation that I started off with. I solved the solution. This is what I got. So basically, if you look at it, you start off, so with limited growth, you start increasing really, really rapidly, and then it kind of levels off because there's this, you have a maximum. Okay. One way that you can kind of explain this is information spread by the media. You know that the media initially, when it go, like if it's something is spread during in a radio or on TV, it gets spread really, really quickly. And everybody starts knowing about it, but there comes a point in time where this kind of starts leveling off, where kind of everybody already knows. Like for example, the coronavirus in the beginning, everybody was just knowing about it. Now at this point, I think no one, we've reached that maximum. I think everybody is aware of that virus. So same thing with memorization. If you're memorizing words, you tend to be very good at it, and then you kind of go through this mental blockage where you cannot memorize any more words. So that can also be described as limited growth. Initially, you start off at 0, and then it just increases really, really sharply, and then it kind of just levels off. Okay, so now we have the last one, which I'm actually not going to solve for you because it involves a lot of calculus and some partial fraction decomposition, and we have the logistic differential equation, logistic growth. So it's kind of like a combination of the first one and the second one. Okay, so we have the third one, which is what we're going to call logistic growth. Okay, and what basically logistic growth means is that now some quantities grow in proportion to both their present size and their distance from an upper limit m. And actually, logistic growth is actually better, I think, than limited growth. Basically, what it does is that you have two different things. So in the beginning, if you think about unlimited growth, everything was based on its present size. In the beginning, we had a certain amount, and then it's just growing forever. Okay? Then with limited growth, we said, okay, well, let's say we start at 0, so we don't have a present amount, okay? And then there's a maximum, okay? There's a maximum that I cannot grow anymore. In logistic growth, it's saying that now I have a present size and I also have a maximum. So basically, my differential equation is incorporating the fact that I have a present size, that's basically the unlimited growth, and I also have my limited growth. So both of them are comprised together. So if you kind of think about it, you're first exponentially growing. Okay, so it's growing exponentially. Okay, so you have some sort of growth, and then after that it starts leveling off. So it kind of looks like this S shape into some value m. Okay, so logistic growth is actually used a lot, and I'm not going to give you the solution to it. Well, I will tell you the solution, but I'm not going to derive it. The solution is y equals m over 1 plus c e to the negative a mt. That's basically what it is. And the way that we figure out the c value is with initial conditions, which can be really, really complicated at some point and a lot of messy algebra. Okay, so this c is going to depend on what on what the initial conditions are. Okay, sometimes they might give you one, sometimes they might give you two. It can get really, really messy if and I'll show you an example of that. But some examples of like a logistic growth, if I go back up, it's basically confined populations, kind of what we were talking about. Like if I have a certain amount of bacteria or animals, and then we have some predator stuff. Epidemics, so rumors, total sales. So logistic and limited sounds very, very similar. The only thing that you have to be very careful with is that this one starts at 0 and this one doesn't start at 0. This one has some present time. We have some amount. So that's kind of how you can differentiate between the two. So in the next video, we will talk about the differences between all three, do some problems, and then do some applications.